All right, so our chapter is about equilibrium. So what is the big thing that stands out to you when you guys have seen, not the word, when you guys were looking at these new types of chemical reactions? What?
The bar that goes both ways.
The arrow goes both ways, yeah. So let's go ahead and make sure we draw an arrow going both ways. Okay, it'll either look like that. That's usually what I do when I hand draw it. If you would prefer this, you can do that too. It doesn't matter. They both mean the same thing. It just means going either way.
If you would underline equilibrium and then put the arrows on the side.
It would be. That would be.
That's a missed opportunity right there.
Like there.
Yeah, but it's too late now.
All right. So the big thing about equilibrium is that you have what? Two what?
Products?
Actually, I shouldn't say two.
More than one.
Let me take that back. Don't write two. Let's say a forward. Sorry. And reverse reaction happening. Who can finish that sentence? Simultaneously at the same time. More importantly, at equal rates. Okay? Remember, in the video that we watched on Friday, it was about how fast they were filling up the hole or digging the hole. Right? And so we have this forward and reverse reaction happening at equal rates. That's when equilibrium is established, okay? Things don't automatically just start out in equilibrium, though, all right? So they have to build themselves to that, and that's what we're going to kind of talk about here. What I'd like you to do is underneath this, draw yourself a little graph, okay? Let me make sure I'm still on the screen. There we go. And on your x-axis, we're going to go ahead and say time, okay? And on your y-axis, we're going to say rate, okay? So when you have a rate versus time graph, okay, and you want to show that equilibrium is happening, when you have a reaction, okay, is there only one thing that has a rate? According to this. No, there should be two things, right? You have a forward one and you have a reverse one. So we're going to show that forward one, which is going to decrease eventually. And we're going to have our reverse one, which will start to increase. And eventually they're going to meet right here. And they're going to have the same rate going back and forth. This right here is that equilibrium. Okay? The other graph that I do want you to be ready to see, so if you can draw it right next to it, looks really similar, except it's going to have concentration versus time. And instead of meeting, they're going to kind of overlap like that, okay? But still, what you're noticing is it hits a moment where concentration to us is not going to look like it's changing anymore. You see that? It flattens out. So equilibrium is all about that flattening out part, okay? So, question. On this next graph that you guys just drew, which one do you think is representing the reactants?
The left.
The top line or the bottom line? We're talking about just this graph right here. The top one, because it's decreasing, right? So, like we started with all of these reactants, and if we're using them up, hopefully the concentration starts going away. So these will always be your reactants on the top line. And these will be your products on the other one. Sorry. I have to write it off to the side. I ran out of room. Okay. And so I just kind of want you to be ready to see that kind of graph and know that that's what it's showing. Okay? We're not going to do much more with those, so don't worry about it too much. All right. You guys ready? Okay, here, we'll just stay on the same slide. All right, so an important word that we were talking about on Friday was that this whole thing is what? It starts with a D. It's dynamic. Okay? And dynamic means that constantly reacting, okay, or constantly moving, meaning that it is constantly going forward and it's constantly reacting reverse. And that's kind of what you guys were working on with your POGL, okay? Now, if we mess with things, if we say, hey, I'm going to increase this concentration or decrease this, or I'm going to crank up the pressure or the temperature, we can shift this thing reverse or forward in order for it to get to a point where it wants to reach equilibrium again, okay? And I just need you guys to be familiar with what you guys were doing on the POGL, which is if I say I increase concentration, which way does it go? I don't need any more details than that, okay? So as long as you were kind of starting to get it with the table that you guys had to do, you're in a good spot so far, okay? You're welcome. Okay, so okay. So now I want you to write your equilibrium chemical equation. Okay, this is a general outline of an equation, meaning I'm not going to put actual elements and things in there. What I'm going to do is I'm going to say little a, big A, plus little b, big B, forward, backward, gives me little c, big C. Okay? So if this is my general chemical equation, okay, this is kind of like what we had in our warm-up right here, okay, and I were to ask you for the equilibrium expression or equilibrium constant, I'm kind of asking for the same thing in both of those. Okay? Then you're going to set up a little equation. All right? Your constant is going to be a K. It's going to be a big K. Now, for your guys' purposes, we're just going to go KEQ. Okay? But when you get to AP here, there is KC when you're talking about concentration. You do not have to write all these K's down unless you really want to. If you're going to AP, I would write them down. Or if you plan on doing AP at one point in your life. Chemistry, yes. Okay. But otherwise, just take this in, okay? So you would have KP if you were talking about pressures. You would have KW if you're referring to the ionization of water. Ka if you're dealing with acids. Kb dealing with bases. Ksp. Is there 7 there total? Okay. I believe I got all of them. All right. So there's all these different Ks. Okay, and it's all based around the same idea of what I'm about to show you is how this expression is set up. The one that you guys, I do need you to be familiar with is going to be Kc and Ksp. Ksp has to do with your solubility. Kc, like I said, we're going to deal with mostly concentration. I probably won't make you guys do the pressure too much. When we get to acids and bases, you guys will be using these, but you aren't going to have to calculate it the same way. Okay? All right. So this little expression, it's going to look like this. So I'm going to go ahead and write it out for you, and then you guys are going to tell me what is that general rule? What is it actually doing? So it's going to look like this. You're going to have brackets with the big C to the little c, all over brackets with big A to the little a, and big B to the little b. What do the lowercase letters represent? Coefficients, exactly. So we're going to be putting them to those exponents. Who can remind me what the brackets are representing? He was right, sorry. Concentration. Okay, what's the other word? What have you guys had to calculate recently? What is concentration? Starts with a big N. Molarity, right. So this is where that moles over liters is going to come into play. That's all that those brackets mean. That means that if I give you information in moles, you can't plug it into this expression. You got to know how much you're dealing with, get that concentration, and that's what goes in here. Because this little equilibrium value is very specific for each type of equation. No matter what, you're going to have the same ratio of concentrations because it is what it is. I know it's a horrible explanation, but it is. All right. We have a whole list of a bunch of values, especially when we get to the KAs and KBs. Okay. My AP kids have to refer to like 4 pages of these lists in order to get these values that they need. Okay. So we have that. We said that these little letters are coefficients. Okay, and so you're just changing those coefficients into exponents, and that's what's going to help you get this value. Okay, so what exactly is this expression showing? Who's on top? The products, exactly. So we're going to have concentration of products always over concentration of reactants, meaning that if you have a K value that's going to be greater than 1, it's going to mean something. If it's less than 1, it's going to mean something else. Okay? And we'll get there in a second. Never include solids. Okay? Because solids don't depend on concentration. A solid is a solid is a solid is a solid. You can't change its concentration. Okay? I know, right? It is what it is. There you go. So, you also cannot include pure liquids because a pure liquid is a melted solid. Once again, concentration is never going to vary. It is what it is. Okay? The only things that get included in this are going to be gases or aqueous. Because what does aqueous mean? Do you guys remember what aqueous means? Aqueous means it's mixed in water, right? It's you can put a certain amount of solute into a certain amount of water to give it a certain. What'd you calculate last test? It's up there. Molarity, exactly. Molarity varies when you're dealing with aqueous things. So never include solids and liquids, and for the most part, that's water, unless you're dealing with what we had in the warm up. Okay. All right. Last little bit that I'm going to have you guys write is going to be cool. You guys got through it all. Okay, right underneath this, I want you to say, okay, so if K EQ is less than 1, it's smaller than 1, it's a decimal, okay? So that means like 0.00001, right? It's less than 1. Who does it mean you have more of, products or reactants? I want you to think of it. If I have something less than 1. Okay, so let's try this again. If I do 2, listen to this. If I do 2 divided by 1, what's that answer? Ready? If I do 2 divided by 1, what is that answer? That equals 2. If I do 1 divided by 2, what's that answer? 0.5. Okay, so which one of these is less than 1? The half. That's what I'm talking about here. So who did I have more of? The who? Reactants. Right. So if you have this, that means that you're favoring reactants. And you have to be able to tell me that. Okay. And tomorrow, because I think we might run out of time in a second. Oh, no, I have a little bit of time. I'll show you what it means for solubility. If we have KEQ greater than 1, right? So I could have 5 or something. What does that mean it's favoring? The products. Okay, and if you forget this, please do what I did up here. Throw in random numbers that make sense to you. 2 over 1 versus 1 over 2. Easy stuff. You can definitely picture that in your head. Sorry, it says favorite products. Okay, this next part you don't need to write down, but you can listen. Please watch up here real quick. All right, when we were dealing with solubility, all right, let's say something like sodium chloride. When we put sodium chloride into some water, what's going to happen to that sodium and the chlorine? You guys, is sodium chloride soluble?
Yeah.
Look at your solubility rules. Let's go. Yes, sodium is group 1, always. Okay, if it's soluble, what does that mean in terms of dissolving? Can it dissolve?
Yes.
Okay, when something dissolves, what does that mean?
It splits.
It splits. Good, awesome. That's what I was going for. All right. Ooh, I just gave that a positive. My bad. There you go. All right, so KSP is going off of this idea. Was sodium chloride solid or aqueous when I put it into the water? This little thing. Was my salt solid or aqueous when I put it in?
Solid.
Solid. Good. All right. So when we go to write a KSP, I told you guys this is the one that I want you guys to kind of be familiar with. Okay? What does not get included here? It's solid. These guys are mixed in with the aqueous. So who's going to be in our expression? Products of a reactants. Na is one of them. You got it? Yes. Do you guys agree with this? And that's it? Because we don't put the reactants. Why don't we put the reactants?
Yes.
Because of what? It's what? Because it's solid. It's solid. So KSP is always going to just be your products. This value, if it's greater than 1, what does that mean you're making more of? Obviously. Products. So that also is going to mean, I'm sorry, let me put KSP. KSP is greater than 1. It means it's very soluble. Do you understand why I'm saying that? If it's favoring the products, that means it's favoring the splitting, right? So it's very soluble. So what you guys are going to look at with KSP is that you're going to have very small ones and very, very, very big ones, okay? And that's going to tell you whether it's kind of soluble or whether it's making more of the solid. Okay? Tomorrow's warm-up. That's what it's going to be. Good luck. All right.